Okay. Good evening, everyone. Hey, that's good. This is truly a unique and very present occasion. I'm indeed very pleased and feel very privileged to be introducing Professor Croes Boulanger, an outstanding engineer who's a good friend and a highly esteemed colleague, and with whom I have closely worked for the last 32 years. And what's unique about this occasion is that I am introducing him to receive a medal and present a lecture established to honor an outstanding engineer, the late Professor H. Bolton Seed, who was also a good friend, a highly esteemed colleague, and with whom I had worked very closely for 25 years. This medal is awarded for excellence and outstanding contributions in teaching, research, and practice in geotechnical engineering. Professor Boulanger excelled and continues to excel in all three areas. Permit me to elaborate. Professor Boulanger taught at the University of California at Davis from 1992 and decided to stop teaching, but not quit geotechnical engineering in 2023. He has been an outstanding teacher, culminating in his promotion to the rank of Distinguished Professor in 2020. He has also been and continues to be an outstanding researcher. He has supervised 20 PhDs and 39 master theses. His research, concentrating on aspects related to geotechnical earthquake engineering, covered a wide range of issues critical to increasing the fundamental understanding of such issues and the development of improved methods for practice. These have included contributions to soil-pile structure interaction in liquefied soils, updating and improving the liquefied evaluation procedures, and to other areas related to liquefaction, such as post-liquefaction strength, cyclic softening of clay-like soils, just to mention a few. Of course, the jewel of these activities, that is his research activities, has been the development of the PM4 sand and the PM4 silt, constitutive models that he initiated some 13 years ago and has continued to update and improve together with his colleagues and their students. Practically any nonlinear dynamic analysis worldwide of a soil structure such as an embankment dam uses these models. These contributions have been acknowledged with many rewards. Let me just give you a couple of examples. Election to the National Academy of Engineering in 2017, the Norman Medal in 2006, the Peck Award in 2016, and now the Seed Award, or Seed Medal from ASCE. The Ishihara Lecture in 2024 from the International Society for Soil Mechanics and Geotechnical Engineering, just to mention a few, and many, many more that he has been awarded. Professor Boulanger is also an outstanding engineer practicing in the field of geotechnical earthquake engineering. He has served and continues to serve on technical review boards for very significant and challenging projects in the US and many other countries. And if that's not enough, he gives a great deal of his time and effort to service to technical societies and a number of state and federal agencies. For example, he served as a member of so many committees and chaired quite a few of them for the Geo-Institute, the Earthquake Engineering Research Institute, the ERI, NSF, and HERE, et cetera, et cetera, et cetera. And in conclusion, I should just mention, and I've worked with him really very closely, he has always amazed me. It has always amazed me that Croes could do so many things and do them so well. Croes, the floor is yours.
Brad, I think you're wrong.
Nope. You're wrong. At the end?
There you go. Come on back up.
Yeah, you got to get a picture taken now.
I'm just going with what Brad told me.
I forgot.
Thank you.
My pleasure. Hello, Susan. You should be in the. You should be in the.
There we go. Pick the time. There.
Okay.
Squeeze in together.
Okay.
Yeah.
Thank you. Thank you. Okay, well, thank you, Ed and Susan. I'm very grateful for the introduction and for the opportunity that GI has given me to be able to deliver this seed lecture. So in a minute, I'll be talking about deformation modeling in risk analyses for dams, but I first wanted to relay my story of how I came to know the late Harry Seed. So I'm going to go back to early 1986. I'm April, and I'm trying to decide where to go to grad school in Canada. I went and talked to the late Professor Liam Finn for advice. He was my advisor, and he said, well, wouldn't you rather go to California? And I thought, that's a great idea. So he said, you should write this guy. I wrote 3 letters. I got 2 replies back right away, and they explained that I'd missed the deadlines for applications, and I'd never taken the GREs. I should apply next year. I thought that was the end of my travel south. The phone rings. Gentleman introduces himself as Harry Seed, and he says, I'd like to invite you to Berkeley. We have a fellowship. Would you like to come? And I said, well, is it a problem? I never took the GREs. He says, no, we have an exception. So, okay, I accept that. That's really good. So it's, like 3-4 months later, and I head down from British Columbia down to Berkeley. Now, I have to explain that I went through school on student loans. And you can't get a student loan to go to grad school in another country. So all I had was my income from the summer. And I went down to Berkeley, and I gave all that income to the International House for room and board. And I had nothing left in the bank, and I thought this would be okay. I go to orientation where they explain that the first paycheck comes at the end of the month. And you have to pay your tuition first, and we'll reimburse it with that paycheck. This was a problem because I didn't have that money in the bank. So I wasn't sure how to solve this. I walked out of orientation, and up walked Professor Seed, and he introduced himself. Now, this is the pre-Zoom, so this was the first time I'd ever seen him or met him. And we have a few niceties, and he says, well, how is this going? And I thought, well, if he can get exceptions, maybe he can handle this one too. So I explained to them that I had to pay $800 for tuition, but I don't have that in the bank, and I'm not quite sure how I'm going to do this. But this time he didn't do the exception. He pulled out his checkbook and wrote me a check for $800 on the spot and said, just pay me back when the campus pays you. And so I can say that I was literally indebted to Harry Seed from the moment I met him. Now, I was he was a very inspiring teacher, and I was very thrilled to be able to start my PhD studies with him. Of course, his unfortunate passing meant that I was not able to finish my studies with him. But at the same time, I know that Professor Seed, through those 25 years of work with Ed, had a great influence on Ed's thinking and approach to life. And then in the last 32 years, Ed has had a tremendous influence on me. And so I think, at least indirectly, Professor Seed has influenced my career throughout my lifetime. And so I'm very thankful for the opportunity to be able to give this lecture in his name. So with that, we'll get back to the talk. We're going to look at deformation modeling. It's in the context of risk analyses for dams. If we look at risk modeling for water or tailings dams, and you look around the world, you find a wide range in the complexity and maturity of the practices. In the US, we have pretty well-established guidance for water dams. Internationally, our guidance for tailings dams is more general. And if you look around the world in industry segments, there's a wide range from fairly semi-quantitative all through very rigorous frameworks. And so we have to improve our practices in all these different ways. Now, in any of these cases, if you're looking at a dam of significant consequence, we will end up doing nonlinear dynamic analyses for the seismic part of the problems. And those nonlinear dynamic analyses, or NDAs, the quality of that work is going to depend on the site characterization, where we get our properties, our choice of the input ground motions, which is the loading, the numerical methods and the constitutive models, that's the software we're going to use, and then how we use the software, the protocols for the numerical analysis and calibration of constitutive models. And all of that is going to depend on the expertise of the analyst and their resources, the amount of time they have to do their work, and the quality of the review processes. You're going to take that, and we're going to take those estimated responses, and we have to feed them into the risk analysis, and we have to track the uncertainties. So the uncertainties, we will often break these down into two categories. They will be the epistemic, or the reducible, in principle, uncertainties. And we'll have our aleatory, or irreducible uncertainties. And these are the uncertainties that we will generally evaluate through logic and event trees as part of a quantitative risk analysis, or a QRA, or at least parametrically to evaluate the significance of these uncertainties on performance. But we also have to keep our eye out for errors. And these errors fall in two categories. One category we could call ontological errors, and this is where we've used inappropriate methodologies, relationships, or input models, and that's produced a bias or can throw us off quite substantially. And then there's also human errors, just the blunders, the bookkeeping, which are very easy to make with these complex analyses. And it's the ontological and human errors that we're trying to minimize through our QA and QC efforts. In our experience, what you find is that these minimizing errors is as important to the success of a project as it is tracking the aleatory and epistemic uncertainties. So you really got to track these, and we're going to talk about both of them. And so in putting this talk together, the objective I have here is to share a few lessons that we have learned and the associated recommendations for improving our practice. And these lessons and recommendations are targeted at everyone involved in the work, from the analyst through the managers, the regulators, the review boards, to the owners. So there's a little bit, everyone plays a role in this. And as an outline, I'm going to therefore start with a couple of high-level 30,000-foot comments, and then I'll go into spend some time on logic and event trees. And when we do the logic and event trees, we'll talk about what branches we're going to include and different key uncertainties, and I'll be spending or focusing on what we leave unmodeled. That'll be one of the things we'll focus on. And then we'll put those branches together. We also then will switch and look at the QA/QC processes to minimize those errors. We'll talk about documentation reviews and go over how you can look to find common errors as part of reviewing these processes. And then we'll wrap this thing up. So let's start first with some high-level comments and performance objectives. Now, performance objectives, we always are going to be concerned with life safety, but we're also going to be looking at economic impacts, operations, environmental, community, reputational impacts, and these all can be very important for our owners or our clients. And one of the lessons that you from doing this work is that it's a really good idea to periodically revisit those performance criteria with your client or your owner. And the reason is the objectives aren't something you fix and leave it. What can happen is they depend on your costs and your benefits, and they're going to change as you learn more about how the system is behaving. And so as you learn about the nature of the problem and the cost to achieve certain performance, revisiting with your client about what their real objectives are, they often evolve, and that can help inform a more efficient execution of the risk study. In addition, you got to always be thinking about this as a risk, a system risk, not just a seismic problem. And when you look at the system, you need to think about the contributions to your risk from the operational, the hydrologic, and the seismic loading. And you need to understand the interdependency of the components. So how does the embankment, the tower, the gates, the outlets, the spillway interact and influence each other? And the key out of this is realizing that the optimal solution for one component of the facility, for one of the loading conditions, is not necessarily going to be the optimal solution for the system to handle all the loading conditions. And so you want to look at the system. There's a lot of examples of this. A good one was the Army Corps' recent modification at Isabella Dam. And in the end, having to deal with operational hydrologic and seismic loading issues, they end up modifying both dams with raises and constructing a whole new spillway. The fix you arrive at is different than if you tried to fix any one component on its own. And so the lesson from these projects is that when you're doing a seismic study and you identify a deficiency, don't jump to designing a fix. Pause and re-examine operational and hydrologic risks, and then make sure you know what your whole system is doing before you start spending money on further engineering studies. So with those, we'll dive down now into logic and event trees for the QRAs. What branches are you going to include? Now, conceptually, this is schematic from Becker, right? We're going to go all the way from the earthquake loading, move through the kind of the fragility and performance of the system, and on down the consequences. And when we build these trees, they're very extensive with lots and lots of branches. So they get pretty complicated. What I want to point out is we're going to be focusing only on the segment of the trees for the NDA results, and pretty much focused on liquefaction and cyclic softening problems, because that's when deformations are more significant. That doesn't mean we want to lose sight of the other branches, because that's what we're going to be feeding things into. And in particular, we're going to be focusing our talk on deformations, because it's deformations that we have to propagate down through the other branches for the failure modes, such as overtopping, cracking, internal erosion, concentrated leak erosion, damage to embedded structures, intervention, etc. So we're going to have to track the deformations and pass them down through the system. Now, when we're looking at this, then we're going to have to track the uncertainties, so we represent those in the risk analysis. And if we're looking at liquefaction, the question, well, what are the key properties? Well, usually it's going to include cyclic strength, residual strength, cyclic mobility, stiffness, and damping. They're good candidates. It can be other things like reconsolidation strains or other aspects depending on the problem. And that leads to candidates for your event tree, and you start putting these in. You got ground motions. We often get our properties from penetration resistances, so you'll have uncertainty in those. And then those go into estimates for cyclic strength, the residual strength, cyclic mobility, reconsolidation, etc. We have our stiffness, shear wave velocity, permeabilities, the numerical model, and then other factors. And we're leaving a whole bunch of other factors uncovered. And these include things like, spatial coherence of the motion, drain strengths of the other materials in the embankment, cracking, localizations, mesh effects, 3D effects if you're only doing 2D models, the modeling procedures. So in fact, there's a lot of uncertainties, and the problem quickly gets intractable. And so what we're really trying to do is identify the key ones, keep this a little simpler. So the first thing we got to do is think about, we're going to tackle these problems. You need to identify whether you're working in stable or unstable regimes. There's certain structures where you'll get a lot of deformation, but you remain stable, and there's others where you can go unstable. Now, what the schematic on the right is showing, that top plot is, say a crest settlement versus an intensity measure of how strong we shake the dam. And what you can get is a certain level of shaking. You might trigger an instability, a large or essentially uncontrolled deformation. And we're going to have to treat those unstable cases separately from the stable ones. And so you might track the fraction unstable and then have to have a model to predict deformations for the stable cases. So both of these are very important. Time limits, we're going to focus only on the stable cases as an illustration of one of the things we have to deal with. Okay, so we're going to do this. Imagine that you're going to do you've got a stable system, you've done the sensitivity, you know it's going to stay stable, but you do a sparse tree. And you'll see sparse trees in practice, where maybe you just do ground motions, maybe you look at penetration resistance, and maybe another property. And what that means is schematically you'll have an estimate of deformation versus intensity measure, and you've modeled some variability. And the variability might not be that large. There's all those things we didn't model, the unmodeled uncertainties, and those unmodeled uncertainties can be large. They include all the things we talked about and the shortcomings in the ones in the earlier branches. If you add the unmodeled uncertainties, you're going to have greater variability, and that's going to result in greater risk. So that propagates down the line. So maybe you do a little bit more work, you add some more parameters, you investigate them as part of this event tree, and you're going to have some unmodeled uncertainties at the end, but there'll be fewer of them. That means that if you look at your deformations, you'll have modeled greater variability. You have less unmodeled, which means when you add it, it doesn't widen you as much. But you're in an odd situation here where you've made it so that if someone does additional work, they have more variability and greater risk. And you don't ever really want to be in that situation. So what we'd like to do is think about, well, how can you estimate and account for unmodeled uncertainties, even if you're using sparse trees, different kinds of level of rigor. In order to do this, what I'm going to do is we'll walk through some of the different key sources of uncertainty, get some rough estimates of their contribution to the variability. We'll pull them back together at the end and talk about how we can make this a little bit more reasonable, even when we're using sparse trees. So with that, let's start with one of the big ones, is always the earthquake acceleration time histories. If you look at the variability in dam deformations you get from just the ground motions, it's going to depend on the dam. It's going to depend on what you're looking at, the crest settlement or the toe settlement. So there's some dependence there. It depends on how you pick the time histories, how you scale them, and how you modify them. And the uncertainty in the mean response you get depends on how many of those motions you use. So there's a lot of different uncertainties you can put together. What I find is that if I go back and compile a set of projects performed by various people using what are generally good practices, you'll see that if they used sets of spectrally matched motions, tightly matched motions, you get a standard deviation in log units of about 0.2 to 0.25. If they instead used sets of motions that were scaled to match a spectra on average, but the individual spectra include some variability, you're going to get a higher standard deviation in displacements, maybe 0.3 to 0.35. And then just you recall that these are in log units, so if you took the exponential of, say, that 0.35, you'd get a factor of 1.42. And what this means is that if you had a mean estimate of the displacement, then plus one standard deviation or minus one standard deviation just means multiply that by 1.42 or divide by 1.42. The uncertainty in these deformations are therefore likely underestimated when we're using spectrally matched motions, which we can deal with, but just recognize that. Another big source of uncertainty is just dealing with spatial variability in natural or constructed deposits. And you get a handle on this by using various numerical analyses. This is an example of some work with Jack Montgomery a few years ago. So you look at a response of a dam where you model those stochastic variability in the properties, and then you turn around and model it with uniform properties based on some equivalent representative percentile, and you can compare them. And that work was expanded on by Nick Paul, where we used different height embankments, we used different wider range of properties, motions, etc. And this figure is just one example of that kind of work. And what this figure is showing is for those sets of dams from 5 meter to 45 meter high, those are the different colored symbols. The x-axis is the crest settlement from the stochastic models, so you get a bunch of those for any one realization, one problem. And the y-axis is what you get using a uniform model, in this case with the 50th percentile property. And you see most of the points are pretty close to the one-to-one line. What you see is the blue points are the X's are the tall embankment, and there's a lot less variability in them. And then as you make the embankment smaller, you're making the embankment is getting closer or smaller than the scale of fluctuation, which in the legend for this set of data was a 20-meter scale of fluctuation in the soil properties. And what that tells you, the first bullet there, the variability in deformation increases as the scale of fluctuation increases relative to the scale of your structure. Now, if you change the scale of fluctuation to 60 meters, what embankment is small or big changes, and you have to deal with that. But this does lead to some simple rules of thumb that I'll point out from this slide. If you instead do the uniform model, the y-axis is changed to the 33rd percentile. All that happens is the points moved up because the stochastic models don't change. And if you changed it to the 20th percentile, they'll move up even more, and now they're almost all above the point, and maybe that's a little bit too conservative. And so this is where we have our kind of simple guidelines when you don't have confidence in the geostatistics of scales of fluctuation and whatnot. And that is for a conservative estimate of displacements, it's pretty reasonable to use something like a 30th percentile property. And if you're doing risk, you want to represent the range. So we might use 3 branches and do one branch that's kind of like 25, 30%, one's in the middle, one's up maybe 60, 65, and you kind of reproduce the spread. If you go back and compile these types of studies, what you tend to see, kind of typical values, is that the variability you get in displacements from the spatial variability gives you a standard deviation of about 0.2 to 0.4. And it can get larger if you got really small structures, small levees with big scales of fluctuation. So the special case, but for dams, we're usually looking at something like this range. So these numbers start looking familiar, and we're going to add a couple more. So the next one we go to is model uncertainty. Okay, now model uncertainty, this term refers to just the numerical analysis model, the constitutive model and the numerical platform. No model's perfect, right? Some are useful. So these models, like what's just the error due to picking between different platforms? We can get a handle on this by comparing results when you use 2 or more well-validated models with consistent modeling procedures. And an example of this is, again, some work from Jack Montgomery and Abazadeh. And they looked at the response of an embankment dam, varying the properties of the shell and the alluvium and the motions, etc. The x-axis is showing crest settlement that you get if you use the PM4 sand model. The y-axis is what you got if you used the UBC sand model. And you can see most of the points are kind of within the 0.8 to the 1.2 lines. You see is that if the number of people have done this, it's a good thing to do in practice because it's not hard to swap out the 2 constitutive models, and it gives you a sense of how much it affects your results. And when people have done this, typically, you'll see standard deviations between them on the order of 0.2 to 0.3. Okay, so now, what have we left unmodeled? Well, that long list we talked about. And we're not going to go through all these other than to say we leave a lot of uncertainties on the table. And they're going to depend on the individual structure. So like one of the bullets is, the applicability of a correlation for a challenging soil, a gravelly soil, a clay sand. Well, the more unusual your soil, the more uncertainty you're going to have. 3D effects might not be large for one dam, it might be more significant for another dam. So they're going to depend on the facility. But they're not zero. So we're going to try to estimate these. It's going to require some subjectivity. It's going to depend on the project. You can be informed by results of other people's studies. But again, I just want to emphasize that an uncertain estimate of these is better than assuming they are zero. In fact, estimating them as zero is probably the worst estimate you could make, right? So we're not going to do that. So for discussion purposes, these are subjective estimates made for an embankment dam. And on here we have low, medium, and high standard deviations. So the first bullet is the model uncertainty, which we just talked about, say 0.2 to 0.3. The other commonly modeled uncertainties are that big list we just went through, say 0.15 to 0.35. And if you added those together, because most times we're not checking models, so those are all going to be unmodeled, you get something like 0.25 to 0.45. I do have to point out the way we're adding these is the usual square root of sum of all the squares, which assumes that these things are independent and uncorrelated, and that's not true. They will be correlated to some degree, and that will add some additional uncertainty. But it's still better to do anything other than zero. So we're somewhere in the range of 0.25 to 0.45. Now we can pull all these pieces back together. Okay. As we pull them together, first point, again, to emphasize, you have to get the total uncertainty to be realistic to propagate through the rest of the event tree, because all the other failure modes depend on those deformations. So we have to realistic uncertainty to move through overtopping, piping, damage to structures, etc. If you use a sparse tree, you're going to underestimate the total uncertainty, and you are going to underestimate risk. And that's not a good situation. So if you estimate and add an unmodeled uncertainty, it's a pretty prudent and easy way to avoid underestimating your risk. Any estimate for it will be better than assuming it's zero. The second point I just got to remind you is that this all kind of assumes that we've done enough branches or sensitivity studies to identify any unstable regimes, because if you do a sparse tree and you miss an unstable regime, you miss that cliff edge, you're going to underestimate your risks. That's not good. And secondly, you can't just add more uncertainty onto a sparse tree and capture cliff edges. That doesn't do it either. So you had to have checked the cliff edges on your own. So now we get back to this example, pull all these numbers together. Okay, so we start with, for an embankment dam, the uncertainty from the time histories, maybe 0.2 to 0.35. From the representative properties or spatial variability, we said 0.2 to 0.4. The other uncertainties, if you haven't done those, maybe 0.25 to 0.45, and you add those together, you get about 0.4 to 0.7 for your total uncertainty. This 0.7, if you raise it, the exponential of 0.7 is a factor of 2. That's actually quite nice because heuristically, people with a lot of gray hair have been using a factor of 2 for a very long time, right? We always said that if you estimated displacements, you're maybe plus or minus a factor of 2 is about as good as we could do, and it gives some basis for these numbers, how they add up and contribute to that. Okay, so let's go back to what I think we need to do in practice, and that is if you're going to use sparse trees, and the sparsest trees I've seen are like this tree, where you just use the input motions, and then you just have a model for penetration resistance properties, and you do the analysis. If you do that, you'll model very low variability, like in the left figure. You might get say, a standard deviation of 0.28. If you take those typical numbers we talked about, all those unmodeled uncertainties can be large. And you haven't done the work, so you don't know what they are, so you've got to be cautious. You have uncertainty in the uncertainties. And so you should use something that's a little bit on the high end, maybe something like 0.6. And if you add that, you get a total uncertainty that's, say, 0.66, and now we're close to that 0.7 we talked about. And that starts to make a lot of sense. So if you're going to, you see anyone doing sparse trees, something like 0.28, no one's that good. Right? So you have to allow for some uncertainty that you've left on the table. Now, if you do better work and you dive in and examine more parameters, you're going to have more modeled uncertainty, like on the left, but you'll also have less unmodeled uncertainty. And when you add the unmodeled uncertainty in this case, your total uncertainty can actually come down. Probably the bigger benefit is that you'll have better confidence in your understanding of the system and where the mean answer is. That's probably your best benefit. But you also get to a more reasonable place where doing more work should, if anything, reward you with bringing down your variability or uncertainty. So just wrapping that part up, key step in this, identify your stable versus unstable regimes, and you got to have done that through either sensitivity studies or pretty detailed branches. And we'll handle those separately from stable cases. What we were talking about was the estimating displacements for stable cases. You have to get the total uncertainty to be realistic, to get the risk reasonable. And I would argue that you should always include an allowance for unmodeled uncertainties. An approximate estimate for unmodeled uncertainty is better than estimating at 0. And a conservative estimate for unmodeled uncertainty is prudent if you're trying to get away with sparse trees. And that'll help us get away from rewarding people for doing the least amount of work. And as a check, when you put it all together, if you're the reviewer or the owner, you want that total sigma in displacements should be something on the order of 0.4 to 0.7 based on dam projects where people have done the work. And if you see anything smaller than that, they're missing something. And again, no one's that good. Okay, so that was QRA analyses. And a switch, now what we want to talk about is minimizing those ontological and human errors. Now, the reason these are a concern is they're a very common problem in our profession. And the first one is the unreviewable report. This is where the consultant writes the report and says, hey, we did these FLAC models. Here's the deformed shape. The answer is 3 meters. You can't review that. You can't tell if it's behaving reasonably or not. It's an unreviewable report. So then you turn around and you push back and you say, well, we need some figures, some intermediate results, show us these things. That leads to the second problem where the supplemental materials come back and now you start spotting significant errors. And if you identify errors this late in the process and you redo the work, you've screwed your budget and your schedule and no one's happy. So this is not a good situation. A third problem is variability in practices. And this is where you get very different results from an NDA analysis when you change your consultant. This happens if you get one consultant to evaluate the issues and they say, okay, you have a problem, you need to fix it. and then the owner hires a second consultant to do the fix, and they build their own numerical model to design the fix, and they get wildly different answers. And now the nature of the problem and the nature of the fix has changed. You have to resolve that before you can go forward. And those problems are usually due to ontological or human errors. And you have to sort them out, and then, again, no one's happy. So fixing these things early on is in everyone's interest. Now, Mike Beatty and I wrote a paper about this about a decade ago, and we called it a reviewer's checklist. And we went through, if you're going to be able to review a report, there were 12 things that we were interested in looking at or talking about. I'm not going to go through all of them. There's 2 things I want to go on to, and one is going to be some comments on what we want to see for calibration of constitutive models, and then one is what kind of results we want included for a particular baseline analysis case. And we summarize those as a recommended standard set of plots that we would like to see. And people often ask, well, why do you want to see all these plots? Well, the reason is common errors usually will pop on one or more of these figures. You just need to see them. Now, if you get an engineering report, and there's many firms do really good work, you get all these figures, there's no problems. And that's often because the analyst has already seen the figure, and any obvious errors have been spotted, and things are fixed, and that's good. When you get the report and the figures are not there, you can't independently check that everything's behaving well, and you aren't necessarily sure that the analyst has actually checked everything. And so you need to see the figures in the documentation. And here, as we're going to go through this, I want to point out the reviewer doesn't have to explain what's wrong. The reviewer only needs to spot that something looks odd. And if you spot something that looks odd, it's the consultant's job to explain or fix them. You just got to learn how to spot odd. So what I'm going to do is we're going to have a little fun. I'm going to walk through a series of schematics. And on these schematics, I'm going to illustrate errors and issues that have been identified during reviews. Unfortunately, these were mostly of that category of getting them after the report's filed, and then they weren't in the report. So these are all real examples. I want to point out that most of these do not require numerical modeling expertise in order to find, right? This just takes the geotechnical background and a little bit of familiarity with dynamics, and you can spot odd. And that's what we're going to try to go through. We're going to start with some figures on calibration of constitutive models. So let's suppose we have a soils where we can do lab tests like clay silts and silty clays. And the first thing is people like to calibrate to the lab test, so they show you a calibration against a monotonic lab test. Well, turns out that lab moduli are often lower than in situ moduli by factors that could be as high as 2 or 3, and so you're going to underestimate the stiffness, and that's going to affect your dynamic response. So yeah, that's a flag. Or they show you a calibration to individual tests, but they don't show you whether the test is representative of the whole data set. So you got to see where are the other data. Oh, they picked the lowest one, or they picked a very optimistic one. So how did you pick these tests? Or they calibrate it to traxial data. But it's a site where the dominant loading condition is more like simple shear. Well, if you're in a clay silt or a sedimentary deposit, simple shear strengths are often about 2/3 of traxial strengths. And there are many constitutive models, when calibrated to traxial, will not predict the correct simple shear strength. They don't do anisotropically well. So you either get the consultant to show you the anisotropic modeling, prove it works, or they end up having to adjust the traxial to simple shear and calibrate to that. If they've calibrated to lab data, because the analyst is interested in that, you want to check, was it consistent with the other data, the field data, the CPT, the vein shears, the stress history, knowing the OCR of the deposits. And you can have lab data that is biased high or low relative to field data, depending on how they reconsolidated and handled the samples in the lab. And so checking, are the lab data actually matching with the field as part of evaluating this calibration is important. It's also important, I didn't mention, but I'll do it in a second, and that is it's important for how they model strength gain under the weight of an embankment. And we'll do that one in a minute. So now, if we switch to cyclic loading, it's all those issues, plus maybe you got to model this cyclic strength curve, and they're modeling traxial data. And again, many constitutive models, if you calibrate to traxial, will not predict simple shear strengths appropriately. So you have to demonstrate the model does, or you correct the traxial to simple shear and you calibrate to it. Another flag is that lab data are unidirectional. We know the field is multidirectional shaking, and we take these strengths and we usually reduce them 5 to 15% for the effects of multidirectional shaking, given we're often using 2D models, and that is often overlooked and missed. You'll see people calibrating to individual lab tests. It looks great to compare them, but which test? You have variability in the results. Did you pick a weak test? Did you pick a strong test? And you can't match them all. There's variability in the results. So it's better to pick the trend and calibrate to the trend. Now, let's suppose you don't have lab data, so we're going to rely on field data. It's pretty common to use CPTs. We like the CPT. And maybe all the soils are calibrated to the cyclic strengths you get from a CPT-based triggering correlation. The problem is it plows through a clay layer, and if you apply these correlations to clays, you're going to greatly underestimate their strength. And that happens all the time. Kind of wrapping this part up, you might see someone do a calibration based on one type of loading. Look, here's my model, I get the cyclic response well. But you want to see the cyclic strength curve, you want to see the monotonic response, and you want to see the modulus reduction and damping responses. And the bottom line is that if your model is calibrated to one of these loading paths, it doesn't mean it's going to do the other paths reasonably. In fact, it can do them quite poorly. That's why you need to show the calibrated model's response under all the loading paths to make sure you're getting reasonable responses. Okay, that was the first part. Now we're going to switch and look at some typical results that come out of these analyses. I got about 12 of these figures where they're just basic figures that we ask for any baseline analysis. And I throw this figure on it. The figures aren't going to have errors in them, but they're the type of figure we would like to see. And then I'm going to flag the kind of errors that you can catch in reviews. So let's just start with basic contours of vertical effective stress. Well, underneath a reservoir at the ground surface, effective stress should be 0. Sometimes you get negative effective stresses. Sometimes you get positive negative stresses, or positive stresses. These are just bookkeeping errors in the input of the boundary pressure from the reservoir and the nodal pressure. Easy bookkeeping mistakes, easy to catch. If you check the total vertical stress just against sum of unit weight times depth, if those stresses are much bigger, let's say you're 20, 30% higher, real common error is you've input the total unit weight for the soil, not the dry unit weight, not realizing that the program is going to add the weight of the water in the pore space separately. And so you can just catch it by checking these things. We like to see pore pressure contours, should match the reservoir on the upside. If you thought you had a drained shell, you should be expecting low pore pressures. Sometimes you will see really high negative pressures just from improper boundary conditions getting saturation and suction up higher than you should. You can get odd pressures along boundaries if the boundary conditions aren't done right. You just want to see something that smoothly varies. And you should always be checking against piezometers for an existing structure. And it's not uncommon to find the seepage models don't match the piezometer data, and you have to have had that check, a reality check. So that's an easy check. We like to see contours of K0 and initial static stress ratio. And I'll just talk about K0. This is a ratio of horizontal to vertical effective stress. We don't want plots of horizontal stress and plots of vertical stress. We want the ratio because it'll stand out. You'll see K0 values of like 10 on an upstream shell on the face. You'll see really low values like 0.1 in a core. You'll see values like -10 underneath the reservoir, right? And what these all are examples where stresses were initialized using gravity turn-on with more Coulomb models, and they had cohesion to them, and they can produce these unrealistic K0 values. Any granular material after drainage and a little creep is going to have K0 values between something like 0.33 and 3. And anything outside of that's a problem, because the next step is you insert the PM4 sand or the UBC sand model, and you will be starting with the state of stress outside the bounding surface, and it's immediately unstable. You can see that when you look at acceleration time histories. So if you pick out some select points, maybe right at the beginning you see some big spikes. Well, they shouldn't be there. You haven't started shaking it yet. Those spikes in acceleration can come from starting the model with K0 values that were outside the yielding or bounding surfaces, and then had to jostle to get back into equilibrium. Easy fix. It can also be somebody wanted to shorten the runtime, and so they truncated the base file without tapering it, and that means the first input point had a non-zero velocity, and you sent a pulse up through the system. You can see big acceleration spikes during shaking. This is usually the user intervening in the analysis to do something. Hasn't told you about it. One would be the base is on a compliant base, and those dashpots will allow the base to bend in space. And if the base bends significantly, they'll sometimes adjust the stresses to unbend it. If you do that sharply, you get a big spike of accelerations through the system. Or you might have been looking at, say, soil cement treatments, and you're going to say, well, what happens if I crack it at this time? Now, none of these are particularly a problem, as long as you know what they are, recognize them, and you can adjust them so you don't cause such a shock in the system. We like to see displacement time histories. And why? Because sometimes they don't stop moving. And they don't stop moving. This can be, again, an example of truncating the input motion at the base and not allowing enough time for the system to come to rest. It can be because you had analysis stop too soon due to mesh entanglement. You could have a local instability, so the thing is actually unstable and keep moving longer than you wanted it. It could be pore pressures diffusing, if you're modeling pore pressure diffusion, and you're getting strains associated with that. And all of those can contribute to why you're seeing movements continue. And you need to get past that to when things stop moving. So maybe you fix that and you got displacements running out in time, and point A there has come to a stable value. And you always say, well, please show the base, because if you see the base, sometimes the base doesn't go back to zero. Again, this is often not a baseline corrected motions, showing up yet again. And that's why we like to see displacements plotted relative to the base. We ask for response spectra. Easy examples, if I look at the crest is the red spectra, or the spectra for the motion at the crest. The black line is what your outcrop motion is. You can look at where the spectral ordinates are amplified the most, and that's an approximate estimate of the fundamental period of the system. And if that fundamental period is bigger than you were expecting, based on simple rules of thumb, that can be because your system is too soft. The moduli are small. This could be real from very nonlinear responses, or it could be a bookkeeping error where somebody's put in the wrong number and you've got overly soft materials or overly weak materials. An example would be moduli based on lab tests rather than in situ shear wave velocities. You compare a free field point and see, well, how does it vary to what my target outcrop was? Well, it could have been a lot lower, and that can be, well, the input motion was input correctly. It's a compliant base. You had to double the stress at the base. They forgot to. Or they did the deconvolution and they did it incorrectly. It can also be that the free field is actually de-amplifying the motions. And that could be realistic, but it could also be a sign of a bookkeeping error where the strengths or moduli got in too low. So you just got to explain this to me. We want to see contours of displacement. Well, displacements at the lateral boundary should be zero, and you'll sometimes see them just flop out to the side, and that's a sign the boundary conditions weren't applied correctly. You'll see base displacements not coming back to zero everywhere along the base, and that could be, again, non-baseline corrected motions. It can also be if the bedrock layer was modeled relatively thin, and it's not a really stiff bedrock, and you can actually stretch the bedrock. And that's something you can fix by just modeling more rock. So that easy fix. And you'll see that in vertical displacements as well. You'd expect them to all come back to zero, but the models can bend in space. And if they're bending too much, you have to model more of the bedrock to suppress that. Two other ones come up is where displacements are dominated by shallow slip. Now, shallow slip, surface raveling, is real, but sometimes it's accentuated too strongly. One way it can be over-accentuated is if you had shells that were more sandy materials, is you didn't account for how the friction angle increases as confining stresses get smaller. And if you don't account for that, then you'll over-accentuate the shallow raveling problems. The same thing applies if you have clay shells. If you decided to model the shell using strength ratios are going to imply zero strength at the surface, and you can over-accentuate shallow slips in those materials as well. Easy things to spot and fix. Okay, a couple more. We like shear strains. Shear strains, well, sometimes you'll see unusual strains near a toe. The toe of an embankment is unstable. Common problem here is maybe the embankment's over a clay layer. Clay layer is characterized as normally consolidated, got an undrained strength ratio of 0.25, and they've applied that for simplicity to the whole clay layer. What that implies is zero strength at the surface, and the embankment on it's got a very weak material right out past the toe. Normally, you're going to have a crust, and the crust is going to be stronger, and you're going to want to include that in the model to avoid accentuating deformations near the toe. The other side of this coin is seeing large concentrated shear strains at depth across the whole mesh. This can happen where undrained strengths were measured at the toe, and that undrained strength was assumed to apply across all elevations underneath the dam. But if it's a normally consolidated clay, the clay will gain strength under the weight of the dam. In this approach, you'll underestimate the strength and you produce weak strength ratios and an unrealistic base isolation. We like poor water pressures. RU max is most common, so we just want to start there where RU max, you might see values of like 1.1. This kind of surprises you. And then you'll see other values, say 0.8, but I got large strains, and I thought I needed 1 to get liquefaction. Neither of these are problems. They're just issues in communication. So the first one, RU max can be bigger than 1 if you have fluctuations in total vertical stress. The easy way to get around that is change the definition to 1 minus sigma V prime over sigma V naught prime, and now RU will never get over 1, and it's easier for communication of what RU of 1 means. The other side, the RU of 0.8 is no problem. If you don't get stress reversals, you can accumulate strains and cyclic mobility in one direction, so there's no problem. These we just need because we're going to compare them to RU values, and RU values in particular, say at the end of shaking. On the downslope side, maybe after shaking, if the system's stable, RU will come back under 1 because if it's carrying a shear stress, it's going to need some effective stress to carry it. What you're looking for is problems like on the other side where the pore water pressures are negative. This can be quite realistic. This can be just that other parts of the foundation have softened, stress is transferred to the zone, and the zone is dilative, so it's dilating and taking up that shear stress. The problem is, if you're not modeling diffusion, you need to account for the fact that water from the reservoir will diffuse into those depths. These are the shallower depths, so it'll diffuse quicker, and you'll lose that negative effective stress, and so you don't want to rely on that for stability. So normally this is something we would fix, so we're not relying on suction to hold ourselves up. Okay, stress strain and stress paths for a few key points. And you can tell why people don't like all these plots, but I'll tell you, they're worth it. You want to see stress ratios versus strain. And you look at these, you could just quickly look at how many cycles and what's the amplitude of stress to trigger strains. Are these what I expected for these materials? It's not a great check, but it'll spot bookkeeping errors. You can see unusual stress paths where there's a strong dilation pulse and the stress path moves to higher effective stress and then never loses it again. This can be a numerical desaturation of the element when you exceed the tensile limit of the water, and it's something that's easily fixed and spottable. Or you'll see strains accumulation unreasonably quickly at really low cyclic stresses, or illogically, like going in the wrong direction. Now, both of these can be incorrect property assignments, and actually in both of them are constitutive model limitations that people found and the models had to fix or recognize them. Okay, so that was my list, and we're getting close to the end here. The point on this is if you get this documentation and you just get these standard figures, it increases the chance the analyst will have looked at them and they will have spotted their own mistakes, and that's important. It facilitates the ability for the reviewers, the supervisors, the boards, the owners, the regulators to look at these figures themselves and be comfortable, right? Verified that, in fact, this thing looks to be behaving properly. It also provides value to the client. The client is likely going to have to revisit these facilities in another 5-year cycle or another 10-year cycle, and having these results in the report provide value to that client in the future, and so they deserve it. In addition, the review processes, they're really important for minimizing the ontological errors, the choices of inappropriate relationships, as well as spotting these errors. Okay, now you finish all this, and you got your risk analysis. What you really want to do now is do the sniff test of whether or not this all makes sense, the robustness of this work. And you want to question a couple things in particular. The first one is the modeling procedures. You want to look at, are they documented? Are they reflective of good practices? Or is this something that's dependent on what's rather opaque work, probably done by an individual in the back room of some office, right? You don't like that. You want to look at the parametric analyses. Did they do enough parameter studies to identify what was controlling the behavior? And then for those controlling parameters, did they look at a range of defensible estimates? Or is this a result that's using a rather narrow viewpoint or the preferences of an individual? Now, if your client is going to be looking at spending tens to hundreds of millions of dollars fixing these facility, They want to make sure that their decisions are not going to be changed by changing one person or a consultant. They want it to be a robust outcome. If you have any doubts, two things. One is you can do an independent review of the NDA modeling procedures. And this has proven really valuable on another project. So just taking one baseline case, having one person independently wade through the file front to back. What it promotes is good sharing of best practices in the community, spotting of errors. It's an easy thing and it gives everyone more confidence that those errors aren't creeping in. The second one can come up when the response is really dependent on something that's like not really well understood in our community. So you can consider engaging a larger group in an expert elicitation for controlling parameters where we're not quite sure what we're doing as a profession, because you don't want it to be driven by one person's preference or point of view. You want it, the owner wants to know, is this a robust decision? And I've seen this change projects pretty dramatically, and is worth keeping in mind if you're on the consumer end of these reports. Okay, we're almost to the end. Conclusions, I got one slide for this. What I was trying to do today, have a little fun, wanted to share a few lessons learned and some recommendations for how we can do a better job in this type of work, deformation modeling, part of risk analyses for water and tailings dams. At a high level, I just want to remind you, keep looking back at the performance criteria. They're not a set it and forget it problem. Keep reevaluating as you learn more about how the system behaves, and always be thinking about risk at the system level. Don't dive into a design on a seismic fix right away without understanding, or there are other problems that need to be fixed at the same time. In terms of logic and event trees, this is where we account for the epistemic and aleatory uncertainties in the usual properties and loadings that we talk about. The branches and the sensitivity analyses, they have to be sufficient to identify if we have any unstable regimes. We need to know if there's any cliff edges. They are very important for assessing risks. So even though we didn't talk about that a lot, that's a key step. The unmodeled uncertainties, though, they need to be estimated and included as a branch to avoid underestimating risk, particularly when we're using too sparse of a trees. And I think it's pretty easy to estimate some of these numbers, and an approximate estimate is better than ignoring it. We then switched, had a little fun looking at QA/QC for deformation modeling, the ontological and human errors, examples of why you want the detailed documentation so that you can look for yourself to see if everything looks good or is there anything odd. Just show me. Last 2 points, the modeling procedures, you want them to be transparent and well documented, and they should be consistent with good industry practices. And the fragility results, they should reflect a range of defensible parameter estimates and not be unduly influenced by any one individual biases. Okay, then I got a couple acknowledgments. When you put these types of presentations together, there's a lot of influences go into it, and probably more people than I'm going to list here. But I presented draws on work and discussions with a number of people, including a number of former students, and I would have to specifically call out Jack, Nick, Patrick, Sean, and Chris as all having contributed in parts of these studies. Of course, my colleagues who I've worked with closely in dealing with these problems, and parts of these problems, including Ed and Bruce and Jason and Katarina. It's friends and consultants who have had the pleasure to work with many projects, and so we've had chances to talk through many of these issues. I mentioned Mike, Rambod, Marty, Tom Less, and Lelio in particular. But it's really all the clients, and it's all the fellow board members that I've worked with, and all the consultants and all the regulators, because really you learn from everybody on these projects. And so this just reflects, I think, a lot of input from a lot of people who I can't even remember to list. Last, I want to thank and acknowledge Harry Seed for accepting my late application, lending me money, inspiring me to pursue a PhD, and starting me on this path. And it really is an honor to be able to give a lecture in his name. Thank you.